People in the future will probably find it easy to travel back in time so they can sample life as it was in bygone days. We can only guess what they'll think about some of our everyday problems, such as inflation, taxes, and, oh yes, vehicle emissions. Regarding the latter, here's some of what they'll be able to hear and see. Vehicle emission controls are designed mainly to reduce emissions of HC or hydrocarbons, CO or carbon monoxide, and NOx or oxides of nitrogen, all classed as air-polluting compounds. Before emission controls were adopted, the exhaust accounted for 60% of hydrocarbons emitted, the crankcase ventilation system for 20%, and evaporation from fuel tank filler cap and carburetor vents for the remaining 20%. The exhaust also included excessive amounts of carbon monoxide and oxides of nitrogen. Presently, crankcase and evaporation emissions are virtually eliminated. Exhaust hydrocarbon emissions are down by about 97%, carbon monoxide by about 96%, and oxides of nitrogen by about 80% from uncontrolled levels. Most service technicians were first introduced to emission controls back in the 60s, when PCV, the positive crankcase ventilation system, became standard equipment on cars. Then, as the years progressed, engine design changes and added emission controls came along with each new model year. So now, we've got several systems, some with electronic controls, all interrelated in their operation. There will probably be other engine and emission control system changes to come, but system operating principles will generally be the same. So this is a good time for a review of vehicle emissions and emission controls. The exhaust emissions of hydrocarbons, carbon monoxide, and oxides of nitrogen are a direct result of the combustion process. So let's take a minute and see how they are produced. Excessive hydrocarbon emission can result from over-rich or over-lean air-fuel mixtures during combustion. Why both? Well, a rich mixture has less air, so there's not enough to support complete burning, and unburned hydrocarbons go out the exhaust. On the other hand, a lean mixture has more oxygen than it needs. This dilutes the gasoline vapor so much that the combustion flame goes out prematurely, and again, unburned hydrocarbons go out the exhaust. Another cause of excessive hydrocarbon emissions is improper ignition timing for a specific driving condition. Here, especially if the spark occurs late in the combustion cycle, the mixture does not burn completely because it did not start soon enough. Next on our list is carbon monoxide, which, as you know, is a poisonous gas. Carbon monoxide emissions primarily result from insufficient air or oxygen in the air-fuel mixture. The third emission on our list is oxides of nitrogen. Nitrogen, of course, also makes up part of the air in the air-fuel mixture. At high combustion temperatures, a point can be reached where some of the nitrogen will combine with oxygen to form oxides of nitrogen. Smog forms in the presence of nitric oxide, hydrocarbons, and sunlight. Ozone and other oxidants are the major irritants present in smog. Carbon monoxide is not a smog-forming ingredient. From all this, you can see that engine combustion factors can greatly affect exhaust emissions, and why such things as the air-fuel mixture, idle speed, and ignition timing must be correct to get efficient combustion and effective emission control. In addition, we have emission control systems which directly affect combustion products in the engine exhaust. These controls include the EGR, or exhaust gas recirculation system, the THERMACTOR system, and the catalyst system. We also have crankcase and evaporation emission controls which return hydrocarbons to the engine for burning with the air-fuel mixture. These controls include the PCV, or positive crankcase ventilation system, and the evaporative emission system. To sort it all out, it's important that you have a basic understanding of all these emission systems and the engine factors affecting combustion, so that you can effectively diagnose and service emission controls. There are many engine factors affecting combustion and therefore also affecting vehicle emissions. Generally speaking, high compression and lean mixtures are used to maintain good performance and fuel economy, while at the same time reducing hydrocarbon and carbon monoxide emissions. However, high compression and lean mixtures can result in high combustion chamber temperatures, which tend to produce excessive oxides of nitrogen. A richer mixture would reduce combustion temperatures, but fuel economy would drop. A lower compression ratio would also reduce combustion temperatures, but vehicle performance would suffer, and hydrocarbon emissions would rise. So we lower combustion temperatures by admitting controlled amounts of exhaust gas through the EGR, or exhaust gas recirculation system, into the engine intake manifold. Then, to reduce hydrocarbon and carbon monoxide emissions, we use a THERMACTOR air system and a catalytic converter system. Because exhaust emissions begin in the combustion chambers, let's talk first about the engine operating factors that directly affect what comes out the tailpipe, beginning with the fuel system. The air-fuel mixture varies as necessary for starting, idling, acceleration, deceleration, cruising, high speeds, and heavy power demands. This is accomplished by conventional carburation or by a single-point electronically controlled fuel injection system. In both systems, an inlet air temperature control system heats incoming air in cold starting and warm-up operation. The system automatically admits direct flow of outside air when heating is not needed. When temperatures are low, a vacuum-operated valve in the air filter inlet duct is positioned to pass inlet air through an exhaust manifold heat shroud. This heated air helps cold fuel vaporize better for more complete combustion and smoother warm-up operation. As the intake manifold and carburetor warm up, inlet air heating is not needed, so the valve in the inlet duct is positioned to admit direct outside airflow and shut off the heated air. This is an important operation. Should the control valve fail to move and admit cold air only, then the engine may stumble on acceleration or stall when slowing down. On the other hand, use of heated air only can cause high temperature after running and hard, hot engine starting. It should also be noted that in cold starting, the air-fuel mixture is temporarily enriched by the automatic choke, so that the engine will start easily and run without stalling during the warm-up period. To reduce the increased emissions that occur during the choking period, the choke bimetallic spring is electrically heated to help the choke open fully as quickly as possible. The automatic choke bimetallic spring is preset and normally not adjustable in service. However, proper adjustment of choke pull-down, de-choke, and fast idle cam setting, as well as idle speed and the air-fuel mixture, are all critical to proper engine operations and emission control. As you know, ignition timing also affects engine performance and emissions. The DuraSpark 2 ignition distributor for conventional and microprocessor control unit systems has a centrifugal advance unit to change spark timing with engine speed, and a vacuum advance unit to change timing with engine load. Initial timing is factory set and normally not adjusted in service. The DuraSpark 3 ignition system is used with the electronic engine control system, which is called EEC for electronic engine control. In this application, ignition timing control is centrifugal and electronic, and that basically covers the fuel and ignition systems from an emissions point of view. The emission control systems, which can be classified as exhaust emission controls, include the EGR, or exhaust gas recirculation system, the THERMACTOR system, and the catalyst system. Each system works in a different way to reduce the amount of emission products in the exhaust. Let's begin with the EGR system. As mentioned in an earlier section, combustion temperatures are held below the point where oxides of nitrogen are produced by diluting the manifold mixture with controlled amounts of exhaust gas. This is accomplished by the EGR system. The main component of the system is the EGR valve, which is opened by vacuum and closed by spring pressure. The amount of gas flow and timing of the valve cycle are both controlled. In this typical EGR valve installation, we can see the flow from the exhaust crossover passage through the EGR valve into the intake manifold. Generally speaking, the EGR valve remains closed during cranking and when the throttle is either closed or wide open. In this basic EGR system, the EGR valve is operated directly by EGR port vacuum when the throttle is above idle position. Note that a WOT, or wide open throttle valve, is used to close the EGR valve for maximum engine power at or near wide open throttle. And with electronic engine control systems, the valve position sensor signals EGR valve pintle position to the electronic control assembly. This assembly, by means of the control solenoids, directs vacuum to the EGR valve, or vents it to atmosphere. This brings us to the THERMACTOR system. The THERMACTOR system injects fresh air into the exhaust gas after it leaves the combustion chambers. This secondary air reduces hydrocarbons and carbon monoxide by further burning before the exhaust gases reach the catalytic system. A typical THERMACTOR system includes an air pump to maintain a constant supply of air, a vacuum-controlled air control valve which can bypass or switch air output under specific operating conditions, and check valves to prevent exhaust gases from backing up and damaging system hoses or the air pump. The THERMACTOR air pump is a belt-driven vane type with centrifugal inlet air filtration at the pulley end of the pump. The pump supplies air to the exhaust manifolds and to the catalytic converter systems as required. The vacuum-operated air control valve bypasses air pump output under specific operating conditions to prevent backfiring or excessive airflow to the catalytic converter system. A spring-loaded relief valve opens to provide pressure relief if pump output becomes too high. The vacuum-operated diverter section of the valve switches airflow to the exhaust manifolds or catalytic converters as needed. The check valve is a spring-loaded one-way flow device which allows airflow into the exhaust while keeping exhaust gases out of the air delivery part of the system. Now we come to the catalytic converter system, which helps to further reduce exhaust emissions. The converter is mounted in the exhaust system ahead of the muffler. Its function is to continue the additional oxidation or burning started by the THERMACTOR system. The main converter unit is made up of one or two sections, depending on the application. In our example, a TWC, or three-way catalyst, speeds up oxidation reactions to hydrocarbons and carbon monoxide and also reduces emission of oxides of nitrogen. Then, a COC, or conventional oxidation catalyst, further reacts with the remaining hydrocarbons and carbon monoxide in the exhaust gas. Single-section converters are of the COC type. THERMACTOR air is diverted from the manifold to the main converter to increase thermal reaction in the COC catalyst when needed. To protect the catalyst against overheating, all THERMACTOR airflow is cut off anytime the engine is running rich, as in any abnormally hot or cold operating condition. An auxiliary LOC, or light-off converter, is used in some installations ahead of the main converter. The LOC is located near the exhaust manifold outlet, where it can heat quickly and begin its catalytic effect before the main converter heats up to maximum efficiency temperature. Catalytic converter units require no servicing in normal use. However, overheating can damage the internal parts, and complete replacement will be necessary. So, as you can see, the catalyst, THERMACTOR, and EGR systems function very differently, but all work together to reduce combustion products in the exhaust. The crankcase evaporative emission controls consist of the PCV, or positive crankcase ventilation system, and the evaporative emission system. Both of these systems reduce emissions by feeding vapors back into the engine for burning. The PCV system basically redirects crankcase vapors and exhaust gas blowby that would otherwise escape into the atmosphere. This system draws fresh, filtered air into the engine, where it mixes with crankcase vapors. The mixture flows out through a PCV valve, or a fixed orifice, which meters airflow into the intake manifold. The valve both regulates airflow and prevents backfiring into the crankcase. At idle, when manifold vacuum is high, the PCV valve reduces system flow to a minimum. This purges crankcase vapors without upsetting the idle operation or producing excessive hydrocarbon emission in the exhaust. At wide open throttle, manifold vacuum is low, so vapor flow through the PCV valve almost stops. Instead, the vapor flow reverses out through the inlet hose into the air filter and carburetor, where it is carried into the intake manifold. Incidentally, this reverse flow also occurs when the PCV valve sticks closed or its connection to the manifold is clogged. In this case, you'll find crankcase oil in the air filter at the inlet connection. If the PCV valve sticks open, idle operation will be rough and the engine may stall. The crankcase ventilation system on some engines uses a flow-limiting orifice to regulate the system. At idle, the flow may be more than needed to handle the vapors, so some air may also be drawn into the intake manifold. At higher speeds, direct vapor flow into the manifold is limited by the orifice, so the remainder is drawn into the air cleaner. The evaporative emission system is somewhat different. Here, the fuel vapors from the fuel tank and the carburetor are vented into a charcoal-filled canister in the engine compartment when the engine is stopped. Gasoline vapor trapped in the fuel tank leaves the tank through a vapor separator in the top of the tank, and then flows through a connecting tube to the storage canister. When the engine is started and it reaches the operation mode most efficient for purging the evaporative system, the vapors stored in the canister are drawn into either the intake manifold or carburetor air cleaner, depending upon the specific installation. This, and what we've already covered, wraps it up for crankcase evaporative emission controls. Complete understanding of these controls, as well as how the other emission control systems function and work together, will help you to use a total systems approach for servicing and diagnosing emission control problems. Understanding how systems function is an important part of good diagnosis and service, but you'll still need some tools of the trade. These tools are the many reference publications that are available to help you to diagnose and service vehicle emission systems. Here's an important one: the Engine Emissions Diagnosis Manual. This edition is separated into 2 books for your handling convenience. Book 1 covers emission systems and system components used both on passenger car and truck installations. Book 2 covers the electronic engine control system and the microprocessor control unit. Book 1 has an introduction section which gives a description and location of the Vehicle Emissions Control information decal to help you find and understand the servicing specifications and system schematic information it displays. Also included is the location of the engine code information label and the engine calibration number on the label. This information is needed to find the correct service specifications for each engine calibration. Following the introduction section, both books have a diagnostic routines section. Each diagnostic routine is indexed with a routine number, title, and section reference page number. After the diagnostic routines, there is a section covering emission-related components. Each component is identified by title, basic part number, and the symbol shown on the system schematic. In addition to the engine emissions diagnosis books, there's also a summary of final 1981 emission system schematics and specifications now titled the 1981 Engine Emissions Facts Book. As with previous editions, the procedure for using this book requires only 4 simple steps. Determine the vehicle calibration number, check the schematics, refer to the parts list, and use the specifications. Engine Emissions Facts Book pages are indexed by engine family and vehicle calibration number. If you have this information, you can go directly to the index and locate the page number you need. Or you can follow the procedure on the How To page to determine the vehicle calibration number. The Facts Book pages now have the information for each engine calibration on facing pages for easier reference. It is very important that correct part numbers are used to order replacement parts. Some parts may have the same name and appearance as others, but are different internally or in calibration. Such parts are not interchangeable under any conditions. Also new is this symptom-oriented diagnosis guide. It is designed to help you quickly locate and correct the most frequent causes of drivability complaints. Symptoms are listed in the index on the inside front cover, along with directions for using the guide. Each listed symptom is covered in a separate section, which contains common checkpoints for symptom causes, beginning with those which are the most common and easiest to locate. And here's the first of the new engine control systems manuals, specially designed to help you understand and apply a total systems approach in your diagnosis and service work. Each manual covers a separate engine family. These manuals cover all the engine operating control systems, including fuel, ignition, and emissions. The controls are shown as they appear on the different versions of the engine family covered in the manual, along with descriptions of normal component functions in all the control systems during 9 different engine operating modes. Remember, when tackling any emissions control or drivability problems, think total systems and how one affects all the others to get a running start on a solution. And be sure to always use the appropriate publication to help you find the solution quickly and easily the first time.